In this video, we are going to find a factorial number and the power of 5 such that the sum is a power of 7. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. One thing that is very interesting about factorials is that if we have some property for a certain number, like say for this number 120, 5 factorial, the last digit is 0, then starting from this number, all the factorials afterwards will end with 0. The reason is that every factorial is the multiple of the previous one. So another thing, for 3 factorial is a multiple of 6, then all factorials afterwards are multiples of 6, etc. So we're going to make full use of this property to quickly reduce many possibilities. Now let's say for a is at least 5. That's the first case. If a is at least 5, then all the factorials end with 0, right? And notice that there's also a pattern for the other terms. Powers of 5, powers of 7. Powers of 5 except for the first one, say 5 to the power 0, which is 1. All the numbers afterwards have 5 to be the last digit. And while for powers of 7, it follows a pattern like this. So we start with 1, and then it's 7, 9, 3, 1, 7, 9, 3, 1, 7, 9, 3, 1, etc. So it repeats every 4 terms. It's a periodic sequence. So we're going to make use of the last digit to reduce some possibilities. Now if a is at least 5, then of course it ends with 0, but notice that because powers of 5 can only end with 1 or 5, so the left hand side will only be either 1 or 5 mod 10, like the last digit is either 1 or 5. So if I write it out formally, it will be like this. A factorial is congruent to 0 mod 10, and then 5 factorial is either 1 or 5 mod 10. So therefore, a factorial, not 5 factorial, but 5 to the power b, then a factorial plus 5 to the power b must be either 1 or 5 mod 10. And that means both the left and the right hand sides have to be congruent to 1 mod 10. And that means b equals 0, 5 to the b equals 1. And we have 7 to the power c to 1 mod 10. That means the index, the exponent, has to be a multiple of 4. Because these terms correspond to powers of 7 with exponents being multiples of 4. So let's see. Then the equation becomes a factorial plus 1 equals 7 to the power 4c. Here I'm using a capital letter C. In fact, I should let like this. I should erase this. And moving on, I have a factorial plus 1 to be equal to a power of 7. In particular, a multiple of 7. That means a factorial has to be congruent to minus 1 mod 7. I have to specify that c is positive, because if c is also 0, then the right hand side is 1, and so a factorial is 0, then we'll have a contradiction, because factorials are at least 1. And so consequently a factorial must be minus 1 mod 7. But now again, starting from this factorial, starting from 7 factorial, all the factorials afterwards are multiples of 7. So that means a can only be 1, 2, 3, 4, 5, or 6. But all of that implies 1 to 6, and but then a factorial plus 1, all these values are less than or equal to 721, but that's less than 2401, or I should say 7 to the power 4. So surely have no solution in this case. So now from this, again, I've already erased all possibilities from a equals 5 onwards. And what's left will be just a equals 4, 3, 2, 1, or 0. Let's move on to the second case, to the other cases. Well, if a equals 0 or 1, I'm going to settle this first, because for both cases a factorial equals 1. Of course, you can say that by the Catalan theorem will have no solution, but I'm going to prove it in a more elementary way. We can actually get this settled by simply looking at the last digit of both sides. So one plus 5 to the power b is either 2 or 6 or 10, while 7 to the power c are 7, 9, 3, 1 mod 10. They can't be equal. So therefore, no solution for this case. Simple. Now, if a equals 2, then 2 plus 5 to the b equals 7 to the power c. We can quickly see that b and c are both 1. It's indeed a pair of solutions. Now what happens if b is larger than 1? Then we can tell that all the powers are multiples of 25, and so if we want to show that there is no other solution other than 1, 1, then we should try to take a look at mod 25. So if b equals 1, then c equals 1. Otherwise, b is at least 2, so 5 to the power b is congruent to 0 mod 25. Now notice that powers of 7 can only be either 7, and then 7 squared is 49, and that's minus 1 mod 25. So, well, you can see that the sequence should repeat very quickly. Next one is minus 7, and the fourth one is already 1 mod 25. And because powers of 5 are then 0 mod 25, 2 plus 5 to the power b can only be 2 mod 25. And so you can compare this and this block, and there's nothing in common, and so there's no solution for b larger than or equal to 2. So you can tell that this is the only pair of solution you can find in this case. Next we have a equals 3. Then 6 plus 5 to the b equals 7 to the power c. We can actually use a similar trick as above. If b equals 0, then 6 plus 1 equals 7c, c equals 1. Okay, we have another pair of solution. Well, if b equals 1, then 7 to the power c equals 11, no solution. And for otherwise, the left hand side can only be 6 mod 25. So that means no solution because we can pull this down again. So no solution. In fact, I should also check the b equals 0 case above. But of course, there's no solution. I just add the line to make the solution complete. And for the final case, as when a equals 4, then 24 plus 5 to the power b equals 7 to the power of c. Now for this, we cannot use the mod 25 trick anymore because even when b is 2, the left hand side is minus 1 mod 25, so there is indeed a solution. And in fact, one of the solution pairs for this case is that b and c are both equal to 2. So I have to take mod on some other numbers. And in this case, I'm going for the numbers 6 and 4 because they are multiples of 24. Sorry, they are factors of 24. And when 5 and 7 are taken mod 6 and 4, they have very small numbers. In fact, either 1 or minus 1. So the calculations will be very convenient. So let's see mod 6. We'll have 0 plus minus 1 to the power b, congruent to 1 mod 6. So b is even. And if we do mod 4, again is 0. This time is 1 at the left hand side, congruent to minus 1 to the power of c mod 4. So c is even. Then we can let b and c to be like 2 times another integer, and the equation becomes 24 plus 25 to the power of big B equals 49 to the power of big C. And actually we have 24 plus a square number because the exponent now becomes an even number, so it's actually a square number. So if I move the 25 power to the right hand side, I will have 7 to the power c minus 5 to the power b times 7 to the power c plus 5 to the power b equals 24. Now since we have used the difference of square identity and the left hand side is now of the form like a plus b times a minus b, that means these two expressions have the same parity. So there are not many choices for solutions. One is positive, so the other must be positive. And so we can only have 12 times 2 or 6 times 4. If you solve it, it's just two equations, two unknowns. One is 7, 5 or 5, 1. And of course we reject this because the solution will not be integers. And so therefore B and C are both 1. Small b and small c are both 2. So combining all the cases, we have 4, 2, 2, and then for the case above we have 3, 0, 1, and then 2, 1, 1, and for a equals 0 and 1, and for a is at least 5, we have no solution. So these three triples are our only answers. So we can check 4 factorial plus 5 squared is indeed 49, which is 7 squared. 3 factorial plus 5 to the power 0 is 7, which is 7 to the power 1. 2 factorial plus 5 to the power 1 is indeed 7 again. And so, tick, tick, tick. These are valid solutions.